Alrighty, so today we are going to finish this last part of chapter 6, talking about enthalpy. So we spent the first part talking about thermochem, kind of the important parts of how it's just taking in together energy and chemistry. And then we discussed internal energy, so thermodynamics in the first law, how energy is always conserved, and how we look at energy by defining a system, the object of study, and then everything else is the surroundings. Knowing that the sum of the two has to be 0 because the energy is always conserved and constant. We looked at different energy flows, the 4 different types of energy, kinetic and potential, how potential is like our chemical energy of atoms and molecules, and thermal energy is the energy in atoms and molecules related to temperature, which is related to kinetic energy, the energy of motion. We also discussed heat and work, we quantified them, and we ended with talking about experimentally how calorimetry is a process of understanding different reactions, specifically at constant volume, and how we can find the energy in just heat flow by making work essentially 0. And now we're going to talk about enthalpy. So what is enthalpy exactly? So we've just seen that when a chemical reaction occurs in a sealed container under the conditions of constant volume, right? That's what we saw before this. The energy evolves only as heat. So that's making work not necessary. So basically work doesn't exist because we made volume constant, so everything is occurring in terms of heat. So when a chemical reaction occurs open to the atmosphere, so under conditions of constant pressure, because when you have it open to the atmosphere, the reason it's constant pressure is because the atmospheric pressure pushes down on your chemical reaction, creating an overall constant pressure. For example, in a reaction in like an open beaker or the burning of a natural gas on a stove. So when you have a saucepan on your gas stove, if you have a gas stove, and you're waiting for it to warm up before, you throw your eggs on there to cook them. Just that part of it, right? You're keeping it open to the atmosphere. So that's actually occurring at constant pressure. So the energy can evolve then as both heat and work because it's open. So we've also seen that the energy of a reaction is the measure of total energy change. So we've seen that delta E, right, is total energy change. Both heat and work that occurs during a reaction. But in many cases, we're only looking at the heat exchange, keeping volume constant. So when we burn natural gas on a stove to cook food, we do not really care how much work is being done, right? So when you're cooking and you want to, make pancakes, you're waiting usually, I've learned this over the years, that a good rule of thumb is to first wait to have your saucepan warm and then throw your little mixture on there for a really good pancake. So basically, when you have your saucepan, you turn it on, you're not thinking and wondering how much work is getting done on this right now, right? You're just thinking, I want this to be a little bit warm so that I can make my breakfast or my lunch or my dinner or snack or have, etc., whatever it is, right? You're just waiting for it to heat up so you can cook your food. So we don't care about the actual combustion work that goes on the atmosphere by expanding against it. We just want to know how much heat is given off to cook the food. So under conditions of constant pressure, we have a thermodynamic quantity called enthalpy. So enthalpy of a system is the sum of its internal energy and its pressure volume. So enthalpy is H, and it's the sum of the internal energy plus the pressure volume. Since internal energy, pressure, and volume are all state functions, enthalpy is also a state function because these are all not path dependent. So therefore, we can change this and say delta H is equal to delta E and P delta V. Well, I actually can define some more things because I know different equations. To better understand this expression, we can say two terms on the right with the help of relationships that we've learned so far. For example, I know that delta E is Q plus W. Right? And I also know that we can represent specifically what this heat is. We know that at constant volume, we say QV. Well, If we represent heat at constant pressure, then the change in internal energy at constant pressure would be delta E is equal to QP plus W. Well, this is constant pressure, since we're thinking enthalpy at constant pressure. Then the change in internal energy becomes this. And from our definition of pressure volume work, we know that pressure external times change in volume is equal to work being done on the system. So it's negative, right? That's just the flip of the work definition. That's where that's coming from. So if you were to replace everything into your reaction, you would get that the change in enthalpy is equal to heat at constant pressure plus work plus the negative work. So then you see that enthalpy is actually equal to heat at constant pressure because the works cancel out. So conceptually, and often even in numbers, the change in enthalpy and the change in internal energy are really similar. They both represent changes in a state function for the system. Internal energy is a measure of all of the energy, so all of the heat and the work that's exchanged with the surroundings. Enthalpy is a measure of only the heat exchange under conditions of constant pressure. So we are not thinking of work at all. So for chemical reactions that do not exchange much work with the surroundings, that do not cause a large change in reaction volume, right? Because volume is expanded due to work, the pressure pushing against it. Usually, enthalpy and internal energy are very identical in value because they then will mainly just depend on heat exchange. But then the opposite of that, the flip of that, is that if a reaction occurs with a significant change in volume because that external pressure pushing against it to expand it or decrease it, you would have a significant difference between the two values. So before we go into that, I kind of jumped the gun here. I wanted to talk about two more terms that we use to quantify enthalpy. So the signs of these enthalpy and internal energies are really important. A positive change in enthalpy means that it's an endothermic reaction, a term you'll see a lot. Endothermic means absorbs heat from its surroundings. Well, when it's negative, it's the opposite of that. So the reaction that occurs in a cold pack. So if you've ever been in a place where you have to crack this little packet and then shake it and then all of a sudden it's cold, is an endothermic reaction. So it's often used for if you have athletic injuries in a gym. They have them available if you were to get hurt. What happens is when you break the barrier separating the reactants in a chemical cold pack, the substance mix, react, and absorb heat from the surroundings. The surroundings, including, let's say, the little bruise on your ankle or something if you twisted it playing basketball, get colder because they lose energy as the cold pack absorbs it. So exothermic gives off heat to the surroundings when delta H is negative. The reaction that occurs in a chemical hand warmer, just like the way that we started this exact lecture, is an exothermic reaction. When the reaction takes place, heat is given off into the surroundings, including your hand and glove, making them warmer. When you are burning on a natural stove, that's an exothermic reaction because heat is given off. So let's practice all of that. Identify each process as endothermic or exothermic. Sweat evaporating from your skin. Would that be endothermic or exothermic? Sweat evaporating from your skin, what does it do to your skin? It cools your skin, right? Your skin cools down. Therefore, what it means is that you had to absorb heat in order for your skin to cool down, so that's an endothermic reaction. The skin must supply heat in order to create waters to evaporate. Endothermic. Water freezing in a freezer. In order to freeze and become solid, all the molecules come together, and they end up releasing their excess heat. The refrigeration system in the freezer must remove this heat from water to continue to then freeze, and so this is exothermic. Wood burning in a fire releases heat and is therefore exothermic, right? Because if you're burning wood, they're just getting hot and they're letting go of the heat inside, and it's releasing heat, so it's exothermic. So this delta H would be positive, and these two would be negative. Awesome. Now, stoichiometry involving enthalpy. So this is a really, really common for the rest of this chapter, is we're going to apply delta H to our enthalpy. Now, one more thing that I wanted to mention is the terms of endothermic and exothermic in a molecular view, then going into stoichiometry. So when a chemical system undergoes a change in enthalpy, where does the energy come from, or where does it go to? So we just described different endo and exothermic reactions, but what are the sources of that energy? We know that emitted thermal energy does not come from the original thermal energy of the system. Remember how we talked about that billiard ball example, and how the total kinetic energy of the atoms and molecules that compose the system is the thermal energy. And the kinetic energy cannot be the source of energy given off in an exothermic reaction, because if the atoms and molecules that compose a system were to lose kinetic energy, their temperature would fall and the system would get colder. So we know that in exothermic reaction, the temperature of the system and the surrounding rises. So there must be some other sources of energy. It's not as simple as just thinking thermal and kinetic energy in atoms and molecules. So if we go back to just thinking about kinetic and potential energy in a chemical system, we know that potential energy is a source in an exothermic chemical reaction. Under normal circumstances, chemical potential energy, sometimes known as chemical energy, rises primarily from the electrostatic forces between the products, the protons, and the electrons that compose them. So basically, what I want you to think of is the energy needed for a reaction to occur. It is both potential and kinetic. It is both thermal and chemical. You have to think about what is happening to the atoms as they are breaking in a bond and as they're coming together to form another bond. What happens to the reactants? What happens to the products? What makes them release or gain energy? Thinking of stoichiometry, we think of the enthalpy change for a chemical reaction is usually termed delta H reaction and depends on the amount of reactants that actually react. The magnitude of this value reflects the stoichiometric coefficients of the reactants and the products. So if you look at this chemical reaction, I actually have a lot of information. You first want to make sure, if you're thinking stoichiometry, that your equation is completely balanced. And then you know, well, for propane, I have 1 mole of propane that produces negative 2,044 kilojoules. I have 5 moles of O2 that produces negative 2,044 kilojoules. Now, this can be used as a conversion factor because you can say negative 2,044 kilojoules per 1 mole of propane. Negative 2,044 kilojoules per 5 moles of oxygen, etc. So depending on what you're solving for, if you're solving for heat, if you're trying to go backwards and figure out the mass, the atoms, etc., the moles, you can use this as a conversion factor. The best way to kind of analyze that is through right away a problem. Nitromethane burns in air to produce a significant amount of heat. Here you have your balanced reaction. How much heat is produced by the complete reactions of 5.56 kilograms of nitromethane? So you have 5.56 kilograms of this, and you want to know how much heat is produced. I know my total heat of my reaction. This can always be per mole of the reactants or even the products. So I need to go to moles. 5.56 kilograms times, if I want to go to moles, I need my molar mass, so I have to first convert to grams. Awesome. And then I calculate my molar mass. And then I'll write 1 mole of CH3NO2 over 61.044 grams. Now I have kilograms gone, grams gone. Now I can find my heat, negative 418 kilojoules per 2 moles, since there's a coefficient of 2. Nitromethane, 2 moles of nitromethane cancel out. You're left with negative 64577.026 kilojoules, which would be negative 6.46 times 10 to the 4th kilojoules. So nitromethane, 5.56 kilograms of nitromethane, produces this much heat for this particular reaction. Now you can see how you can use enthalpy of a reaction. Again, the reaction is for the entire reaction and applies to the different amounts made and reacted. Let's try another one. So this is also supposed to be propane. So propane and oxygen are combusting here, and you have your enthalpy of your reaction. If a pork roast must absorb 1.6 times 10 to the 3rd kilojoules to fully cook, and if only 10% of the heat is produced, that's actually absorbed, what mass of carbon dioxide emitted into the atmosphere is occurring by grilling this pork roast? So we want mass of carbon dioxide. We're given that we have, if a pork roast must absorb 1.6 times 10 to the 3rd kilojoules to fully cook, and if only 10% of heat produced is actually absorbed by the roast. So we have to think. We know we have that amount of heat, so we're starting with heat, 1.6 times 10 to the 3rd kilojoules, and we want to go to CO2. That means I have to look at my relationship, which is negative 2,044 kilojoules for 3 moles CO2. Now, the tricky part here is that I have this 10%, because it says only 10% of heat is produced. So it's not the full 2,044. So you should take 10% of the negative 2,044 kilojoules before plugging everything in. So we never use a percentage, so you divide by 100 and then multiply it by that number, which would be negative 204.4 kilojoules. Then you can use it. So you can say 3 moles of CO2 over negative produced and absorbed. Would I have negative or would I have positive? Since this is saying absorbed, the actual amount that's absorbed, it is a positive number. So again, 10% of it, the 3 moles comes from CO2. That gives me 23.48 moles of carbon dioxide. Since I want the mass, I would then multiply by my molar mass. Now that's a really large number, so I'm going to convert to kilograms, and I only want 2 sig figs, so 1 kilogram of CO2 was used. It was emitted, right? That's the amount of grams that was actually made in the end. Again, 10% of it, right? We were given the heat, but we had to use only 10% of it. We know the ratio of the different moles. The reason it's positive is because it specifically says absorbed here. So this brings me up to how we can calculate this in lab. So this is a lab setup that you would have done if we've done the Hess's Law lab in person, and this should help you with understanding the Hess's Law lab a little bit more. Constant pressure calorimetry. So for many aqueous reactions, we can measure the enthalpy of a reaction by using a coffee cup calorimeter. It's a really easy setup. The calorimeter itself consists of 2 styrofoam cups, like you can see in this picture, one inserted into the other. And the reason that there's 2 where one is inserted in the other is to help insulation. So it provides insulation from the lab experiment. isolating it from any outside atmosphere or moisture. The calorimeter is equipped with a thermometer and a stirrer. Why do you think having a thermometer and a stirrer is important? Well, if you have a thermometer in your reaction, you can see the temperature change. If you're putting two aqueous solutions together, and if they react, you can see how much heat is being gained or lost by observing the change in temperature. A stirrer is important if you have two liquids together. Because of different densities, sometimes they can have different layers, but we want them to constantly mix to give us the most appropriate results. The reaction occurs in a specifically measured quantity of solution within the calorimeter, so that a mass of solution is known. During the reaction, the heat evolved, or also known as absorbed, causes a temperature change in the solution, which the thermometer helps us measure. If we then know the specific heat of the solution, normally assumed to be that of water, because if you think usually when we put aqueous solutions together, we form water, the specific heat of capacity of the solution can then be used to find the heat absorbed or lost by that solution. So what equation have we learned where we can use the heat, mass, specific heat, and change in temperature? Q is equal to MCAT. Great. So then Q solution can be calculated by the mass of solution times the specific heat of solution times the change in temperature. The insulated calorimeter, and note that we usually have a lid, again, to help any moisture from the outside affect our reaction, prevents heat from escaping. So the insulation prevents any heat from escaping, these two styrofoam cups. So if they're completely isolated, my solution can be assumed to also be my reaction. We can assume that the heat gained by the solution equals that lost by the reaction, or vice versa. So heat of the reaction is the reverse of heat of the solution because of the insulation of the cups here. So because the reaction happens under conditions of constant pressure, open to the atmosphere, because again, there's holes, so it's not like we're completely isolating the pressure or keeping the pressure contained. It's completely constant to pressure. We know that then the heat of the reaction is equal to heat of constant pressure, and I know heat at constant pressure is equal to the enthalpy of a reaction. This measured quantity is the heat of the reaction for that specific amount, which again would be measured ahead of time experimentally, of reactants that then reacted. So to find the enthalpy of a reaction per mole of a particular reactant, we can then divide by the number of moles in a specific chemical equation, which we did prior to this. So again, a little summary of calorimetry. Calorimetry is the way that we can measure energy and heat, specifically heat. A bomb calorimeter occurs at constant volume, and we can measure the internal energy. Coffee cup calorimetry occurs at constant pressure, and we can measure the enthalpy. That kind of summarizes our calorimetry. So the insulated calorimeter prevents heat from escaping. So we assume that the heat gained by the solution equals that lost by the reaction. And because the reaction occurs under constant pressure, we know that heat of reaction is equal to heat of pressure, which is the change of enthalpy in the reaction. And then we can apply that to the different moles of the reactants that actually reacted in a stoichiometry equation. So again, best way to practice is to do a problem. So let's do this problem here. Zinc reacts with hydrochloric acid to form zinc chloride and hydrogen gas. When 0.103 grams of zinc is combined with enough hydrochloric acid to make 50 milliliter solution in a coffee cup calorimeter, all of the zinc reacts, raising the temperature of the solution from 22.5 degrees Celsius to 23.7 degrees Celsius. Find the enthalpy of reaction knowing the density and the heat capacity of the solution. So you're given here volume of solution, which is 50 milliliters. You have the density of solution, which is 1.0 grams per milliliter. Specific heat of solution, which is 4.18 joules per gram degree Celsius. You have the initial temperature, the final temperature. You have mass of zinc. So let's read that again to understand what happens. 0.103 grams of zinc is combined with hydrochloric acid and makes a 50 milliliter solution. That's placed in a coffee cup calorimeter. So we have this now. These are my 2 insulated cups, coffee cup calorimeter, the zinc, it dissolved. Here's then my 50 milliliters of solution. Then at first my temperature was one thing. Once the zinc and the hydrochloric acid mixed, my temperature was another. I want to know the heat of the reaction total. Well, I want to know it for zinc, which means that I know I can find my heat of reaction by taking the sum of the heat of reaction per mole of zinc. Well, I can find moles of zinc by taking 0.103 grams and dividing by the molar mass. That would be 0.103 divided by 65.38 is 0.00157 moles. Awesome. So now I need to find heat of reaction. Well, since I have all the information of my solution in my coffee cup calorimeter, I know I'm at constant pressure. I know my heat of reaction is equal to my heat of constant pressure, which is equal to the heat of the reaction. And I know that the heat of the reaction is equal to the opposite of the heat of solution. One's absorbing, one's releasing. Again, the magnitude never changes. Well, I can find my heat of my solution through MCAT. Because I have my specific heat, I have my change in temperature. Do I have my mass of my solution? No, but do you see how I have volume and density? Can I find my mass? Yes. If you take your 50 milliliters, I mean, you really don't even need to do this calculation, but just to show you, 50 milliliters times 0.1 gram per milliliter, you get 50 grams. Awesome. So now you have your mass of solution. So then 50 grams times 4.18 joules per gram degree Celsius times change in temperature. And what I love about this equation, writing all your units, if something's ever not put in correctly, you can easily visualize as based off units. Since you want heat, what unit do you want to end with? Joules. So you want joules. So you need everything else to cancel out. Well, if you plugged it in correctly, grams go away and degrees Celsius go away. Your heat of solution then in the end is equal to 250.8 joules. So the solution absorbed 250.8 joules of heat. That means that the reaction releases 250.8 joules of heat. So then your enthalpy of the reaction, heat of reaction, will be negative 250.8 joules divided by 0.00157 moles of zinc, and that will equal negative 1.59 times 10 to the 5th joules per mole zinc. Oh, I'm sorry that box looks bad, but there you go. So again, putting all the different concepts together to find the answer you're looking for. Again, always going back to solution, reaction, what's happening. If you're at constant pressure, what can you exactly find? And that you can use the enthalpy of a reaction for all the stoichiometric coefficients in a reaction.